Hi, everybody. I thank ICECA for giving me the opportunity of this talk. And the title of my talk is Acyclic Matchings in Abelian Groups. So first, I'm going to outline the talk. We are going to study matchings in the additive group z to the power of n. Then we are going to define and formulate matching property in abelian groups. Also, we are going to study a specific family of matchings called acyclic matchings in z to the n. And eventually, we are going to characterize all abelian groups with respect to the acyclic matching property. Here, I'm going to address some of the motivation behind this line of research. In general, matchings in the group setting are used as a tool to study certain canonical forms, and we are going to specify what kind of canonical forms we are addressing. So the canonical forms that are generic expression for representing symmetric tensors over finite dimensional vector spaces. And everything dates back to 1916 by a question by Wakeford, which is as follows. Question is that which sets of monomials can be removed from a generic homogeneous polynomial through a linear change of variables? And this question leads to the notion of matchings in the additive group of z to the n. And in 1996, Fan and Loshansi showed that this problem can be transformed to the study of certain class of weighted bipartite graphs. Now let us start with the definition of matchings in z to the n. Let us consider two finite non-empty subsets, A and B of z to the n. A matching from A to B is a specific type of bijection F from A to B, such that this additional condition, A plus F of A not in A, holds for every element of A. And if there exists a matching from A to B, we say A is matched to B. And clearly, necessary conditions for existence of a matching are two conditions. First, A and B must have the same cardinality. And second, the second set B should not contain the neutral element of the group, which is specified here, z to the power of n. And in 1996, Fan and Loshansi provided the first theorem in this line of research. So taking two subsets A and B, finite and non-empty, of the same size from z to the n, and assuming one additional condition here, B does not contain the neutral element of the group, then A is matched to B. And also in a similar manner, matchings can be formulated for a general abelian group. And also here we define matching property in the context of an abelian group. That abelian group G is said to have matching property if for every two finite and empty subsets A and B from G with two additional conditions, A and B are from the same size and B does not contain the neutral element of the group, then A is matched to B. In this case, we are going to say that our group G has the matching property. And now, a natural question here is to ask is that whether we can characterize groups with respect to the matching property. And the answer is yes. And the required tools to provide such a characterization are the followings. First, Kneser's addition theorem, and second, the classical theorem of Hall's, which is called Hall's marriage theorem. So let us review Kneser's addition theorem. In the context of an abelian group, assuming that we are dealing with two finite and empty subsets A and B of our group, we can guarantee the existence of a subgroup H of G such that the following two conditions are the case. First, we are providing a bound on the size of the sum set A plus B, and second, we specify this subgroup that we previously obtained. It would be the stabilizer of the sum set. And also Hall's marriage theorem, which is a classical theorem, and there are many versions of it. Here I'm gonna give the SDR, system of distinct representative, type of Hall's marriage theorem as follows. Let us assume that we are dealing with a collection of finite subsets of a set, call it U, A sub 1, A sub 2, A sub n. Then this collection has an STR, meaning a set of n elements, x sub 1, x sub 2, x sub n, such that this set has two features. First, every xi is an element of AI, and second, all xi's are distinct. So such an STR exists if and only if for every sub-collection of our family of subsets here, we guarantee this cardinality inequality. And this condition here is called Hall's condition. And using these two tools, Loshanzi in 1996 characterized all abelian groups with respect to matching property as follows. An abelian group G satisfies the matching property if and only if G is torsion-free or cyclic of prime order. And also back to 2016, together with 2 of my collaborators, we provided this theorem about matchable sets in abelian groups, assuming that we are just restricting discussion to small enough subsets of the group. If we denote by P of G, the smallest cardinality of a non-trivial subgroup of G, and if we assume that the size of our sets is less than this P of G, and 0 is not an element of set B, then we can guarantee the existence of at least one matching from A to B. Before continuing our discussion to specific families of matchings that are called acyclic matching, I just want to mention that matchings have been explored in other settings as well. One setting is non-abelian groups, or we can say general groups, explored by Eliyahu and Lekovi back to 2008, and also in a very nice piece of work by the same authors, matchings formulated in linear version as follows: matching subspaces in a field extension. And the good feature of this work by Eliyahu and Lekovi is that pretty much they build all of the tools required to prove matchable subspaces, like linear version of Kneser's theorem, and also in general additive number theory theorem in linear algebra setting. Also, matchings in the context of metroids was formulated in 2024 by one of my collaborators, Shiraz Erbil. Now let us study a specific family of matchings called acyclic matchings. Let us assume that we have a matching f from A to B. We are going to associate a multiplicity function m sub f from G to non-negative integers as follows. M sub f of x would be the cardinality of all a's in A, such that A plus f of A equals x for every x in G. Here we are assuming that everything is happening within G. A and B are subsets of G. A matching f from A to B is called acyclic if for every matching G from A to B, the same multiplicity function results in the same matchings. And if there exists an acyclic matching from A to B, we say A is acyclically matched to B. And similar to the matching property, the acyclic matching property is defined. A group G is set to possess the acyclic matching property if for every two subsets A and B with these two conditions, we guarantee the existence of at least one acyclic matching from A to B. And again, natural question here is to ask that whether we can characterize all abelian groups with respect to acyclic matching property. So this question was studied in 1996 by Alon, Fan, Kleitman, and Loshanzi, and they characterized the acyclic matching property for the additive group Z to the N. Z to the N possesses the acyclic matching property. And the main tool they used was nice total ordering in Z to the N, which is compatible with the group structure. Now, natural candidate to study acyclic matching property is the group ZP, the cyclic group of order P. And our experimental result showed that for P equals 2, 3, and 5, Z sub P has the acyclic matching property, while for all P between 7 and 19, Z sub P does not have the acyclic matching property. And the complexity of our code was very high. We couldn't go further above, or I would say beyond 19, because even 19 on its own took 3 months to run. So we reached this partial result about acyclic matchings in 2022 by my collaborator, Philo, as follows. So let's consider a subset A of a cyclic group ZP, where P is prime. And let us assume that A satisfies this condition. A intersection 2A is the empty set. And also we have this additional condition on the size of the set A. Also 2A is defined, all A plus A, such that A is in A. Then A is acyclically matched to itself via the identity map. And again, in the same paper with Philo, we proved that if P is a prime and A and B are finite subsets of Z sub P, with the condition that P does not contain the neutral element, and assuming that the size of A and B is sufficiently small, then we can guarantee the existence of at least one acyclic matching from A to B. Very recently, in 2025, together with my collaborator, Peter Taylor, we proved that if we consider this condition, A intersection A plus B equals the empty set, then A is acyclically matched to B. And the feature of this condition here is that in this case, every bijection from A to B would be a matching. So we have many matchings here. And among many matchings, at least one of them is acyclic. And again, very, very recently, together with Taylor, we proved that the cyclic group of prime order, ZP, does not have the acyclic matching property. So this, together with Loshanzi's theorem about the matching property, we give a complete characterization of the acyclic matching property in the context of abelian group. An abelian group G possesses the acyclic matching property if and only if G is either torsion free or G equals Z sub 2, Z sub 3, or Z sub 5. Thank you for your attention.